Hi everyone. In this video, I will be discussing about eigenvalues and eigenvectors. In linear algebra, an eigenvector, or it may be known as characteristic vector of a linear transformation, is a non-zero vector that changes by a scalar factor when that linear transformation is applied to it. Geometrically, an eigenvector corresponding to each eigenvalue points in a direction in which it is structured by the transformation, and the eigenvalue is the factor by which it is structured. Here, this concept of eigenvalues and eigenvectors, they are very much important in linear algebra. Let's see what are eigenvalues and their corresponding eigenvectors. Let A be a square matrix, I be an identity matrix whose order is the same as that of capital A, and let lambda be an unknown. Then matrix A minus lambda I is the characteristic matrix. Determinant A minus lambda I is the characteristic polynomial. Determinant A minus lambda I equal to 0 is the characteristic equation, which is an equation in lambda. Solving the characteristic equation, we get the values of lambda. These values of lambda are called the eigenvalues or characteristic roots. So finding the eigenvalues of a square matrix A, first of all write the characteristic equation, determinant A minus lambda I equal to 0, then solve for lambda. If A be a square matrix of order 2, then we have 2 eigenvalues. Similarly, if A is a square matrix of order 3, then we have 3 eigenvalues. Okay, so this is the eigenvalues. Corresponding to each eigenvalue, we can find the corresponding eigenvectors. These are some properties of eigenvalues and eigenvectors. If lambda is an eigenvalue of A, which is a square matrix, then lambda raised to n is an eigenvalue of A raised to n when n is an integer. K lambda is an eigenvalue of K into A, and 1 by lambda is an eigenvalue of A inverse. Lambda minus K is an eigenvalue of A minus Ki. Determinant A by lambda is an eigenvalue of adjoint A. So if we have eigenvalue of A, then we can find the eigenvalues of A raised to n, A inverse, K into A, adjoint of A, or A minus K from this properties. Similarly, the eigenvalues of A and A transpose are same. The set of all eigenvalues is called spectrum of A, and sum of eigenvalues of a matrix gives the sum of its diagonal elements. If lambda 1, lambda 2, lambda 3 are 3 eigenvalues of a 3 by 3 matrix, then lambda 1 plus lambda 2 plus lambda 3 will be the sum of its diagonal elements of that matrix, and product of eigenvalues will be the determinant of that matrix. These are very important points. Sum of eigenvalues is the sum of diagonal elements of the matrix, and product of eigenvalues is the determinant of the corresponding matrix. Next, we are going to find the formula for finding eigenvalues of a matrix. If the matrix is a 3 by 3 matrix, then the characteristic equation is, that is, modulus determinant A minus lambda I equal to 0 will be lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0, where S1 equal to the sum of main diagonals of the matrix, S2 is the sum of minors of main diagonal, and the S3 is determinant of the matrix. By this terms, we can find the characteristic equation from the matrix itself. If the matrix is a 2 by 2 matrix, then the characteristic equation will be lambda square minus S1 lambda plus S2 equal to 0, where S1 is the sum of main diagonals and S2 is the determinant of the matrix. So from this equations we can easily find the eigenvalues. Next we are moving to problem. If 2 is an eigenvalue of the matrix 3 minus 1 1 minus 1 5 minus 1 1 minus 1 3, without using its characteristic equation, find the other eigenvalues. Also find the eigenvalues of A cube, A transpose, A inverse, 5 into A minus 3i and adjoint of A. Here it is given that 2 is an eigenvalue of this matrix. The matrix is a 3 by 3 matrix, so it has 3 eigenvalues. One eigenvalue is given. So let's take lambda 2 and lambda 3 be the other eigenvalues. So 2, lambda 2, lambda 3 be the eigenvalues of A. Without using its characteristic equation, find the other eigenvalues. So here we are using the properties. Properties means sum of eigenvalues will be the sum of diagonal elements of the matrix and product of the eigenvalues will be the determinant of this matrix. So 2 plus lambda 2 plus lambda 3 equal to sum of the diagonal elements, that is 3 plus 5 plus 3. Okay, that is 2 plus lambda 2 plus lambda 3 is equal to 11. From this we got lambda 2 plus lambda 3 equal to 9, equation number 1. Next we are using the property product of eigenvalues will be the determinant of this matrix. Here the determinant is, this is 3 by 3 matrix, and find the determinant. Then 2 into lambda 2 into lambda 3 is equal to, the matrix determinant is 36. So lambda 2 into lambda 3 equal to 36 by 2, that is equal to 18, equation number 2. So you have equation 1 as lambda 2 plus lambda 3 equal to 9, and the equation 2 is lambda 2 into lambda 3 is equal to 18. Next we are going to solve these two equations. Okay, from this lambda 3 is equal to 9 minus lambda 2. Put this in equation 2. We have lambda 2 into 9 minus lambda 2 is equal to 18, that is 9 lambda 2 minus lambda 2 the whole square is equal to 18. Then lambda 2 the whole square minus 9 lambda 2 plus 18 is equal to 0. For solving this quadratic equation, we got lambda 2 equal to some 3 and 6. So lambda 2 equal to 3. When lambda 2 equal to 3, we got lambda 3 as 6. If lambda 2 as 6, we got lambda 3 as 3. Okay, so the eigenvalues are 3 and 6. Solving 1 and 2, we got lambda 2 equal to 3 and lambda 3 equal to 6. So the three eigenvalues are 2, 3 and 6. Next we are moving to find the eigenvalues of A cube. If lambda is an eigenvalue of A, then lambda cube is the eigenvalue of A cube. So here 2, 3, 6 are the eigenvalues. Then eigenvalues of A cube will be 2 cube, 3 cube, 6 cube, that is 8, 27, 216. Similarly, eigenvalues of A transpose is equal to 2, 3, 6 because eigenvalues of A and A transpose are same. Next, eigenvalues of A inverse. If lambda is an eigenvalue of A, then 1 by lambda is the eigenvalue of A inverse. So here 1 by 2, 1 by 3, 1 by 6 are the eigenvalues of A inverse. Eigenvalues of 5A, that is 10, 15, 30, that is 2, 3, 6 are the eigenvalues of A. Then 5A corresponds, that is 5 into 2, 5 into 3 and 5 into 6, that is equal to 10, 15, 30. So these are the eigenvalues of 5a. And eigenvalues of a minus 3i. Lambda minus k is the eigenvalue of a minus ki. So here 2 minus 3, 3 minus 3, 6 minus 3. That is minus 1, 0, 3. Eigenvalues of adjoint of a, that is determinant of a divided by lambda. So 36 by 2, 36 by 3, 36 by 6, that is 18, 12, 6. So these are the eigenvalues. Next problem, find the eigenvalues of a equal to 1, 4, 2, 3. This is a 2 by 2 matrix, so the characteristic equation will be second degree and it has 2 eigenvalues. Let's see. First of all, write the characteristic equation, that is determinant a minus lambda I equal to 0. That is implies here a minus lambda I means a minus lambda I is equal to, here a matrix is 1, 4, 2, 3 minus lambda into I will be the identity matrix of the same order, that is 1, 0, 0, 1. So this is equal to 1, 4, 2, 3 minus lambda 0, 0, lambda. Then subtracting these two matrices, that is 1 minus lambda 4, 2, 3 minus lambda, only the change in the diagonal element. So a minus lambda I will be 1 minus lambda 4, 2, 3 minus lambda equal to 0. Determinant of this one. Then finding determinant will be 1 minus lambda into 3 minus lambda minus 8 equal to 0. Solving this, we got lambda square minus 4 lambda minus 5 equal to 0. Solving this quadratic equation, we have lambda equal to 5 and minus 1. So these are the eigenvalues of a. Similarly, we can use the formula. That is, for a 2 by 2 matrix, the formula is lambda square minus S1 lambda plus S2 equal to 0. For S1 is the sum of diagonals, that is 1 plus 3, which is equal to 4. S2, that is the determinant, that is 3 minus 8, which is equal to minus 5. So this equation will be lambda square, alternate plus or minus. So minus 4 lambda minus 5 equal to 0. Solving this, we get lambda equal to 5 and minus 1. This is the easiest method to find the eigenvalues. Also for 3 by 3 matrices.